Okay, let us solve this problem on rotation. The problem is one twirls a circular ring of mass m and radius r near the tip of one's finger, as shown in the figure 1. So here this guy is twirling this circular ring at the tip of the finger, and the finger never loses the contact with the inner rim of the ring, and the finger traces out the surface of a cone as shown by the dotted line. So this is the cone which the finger describes while rotating this circular ring, and the radius of the path traced out by the point where the ring and the finger is in contact is r. So this guy is basically rotating his finger in the radius r such that the finger rotates with an angular velocity omega naught. The rotating ring rolls without slipping on outside of a smaller circle described by the point where the ring and the finger is in contact. So this is the 2D projection of the contact finger and the radius of the ring. So this is the path around which the finger rotates and correspondingly make the circular ring rotate. It is also given that the coefficient of friction between the ring and the finger is mu and acceleration due to gravity is g. Then in the problem it is asked to find the minimum value below which the ring will drop. The problem it is asked to find the minimum value of omega naught below which the ring will drop. So let us solve this problem and figure out the minimum value of omega naught. So as we can see that this is our circular ring, and this guy is holding ring at the rim and rotating it in a canonical manner such that the radius of cone at this point is small r, while the radius of the ring is capital R. So at the instant we can say that this ring is basically rotating in a radius capital R minus r. So this ring is performing rotation due to this finger in this radius. So every point is rotating in radius r minus r. Now since every point is rotating in this radius, let us consider a small part of this ring of mass dm. So this is the mass we are looking at, dm. So in this mass let us locate the various forces. So one of them will be the centrifugal force, which will be m omega naught square capital R minus small r. This will be the centrifugal force, and the weight of this ring. So this will be dm because we are considering a small mass dm, and the weight there will be dm into g, and corresponding we will be having a friction because this force, the centrifugal force, is acting as the normal force. So we are having friction at the top, which will be mu times n. Now if we integrate the whole ring performs the same scenario. So we can say that mu times n is equal to dm times g, because this friction is responsible for holding the ring. Now all we need to do is that we need to integrate for whole ring, because every particle is performing the same rotation about this center r minus r. Now the value of normal reaction will be dm omega naught square capital R minus r is equal to dm times g. So let us integrate this. So integral of dm is just from 0 to m. So it comes out to be mu times m omega naught square r minus r is equal to mg. So the minimum value of omega naught from here is, omega naught comes out to be z by mu r minus r to the power half. So this is the minimum value of omega naught, and omega naught should always be greater than this value in order to ring to be hold intact and to prevent it from slipping down. So this is the answer.